We start. Fiona, make sure you mute your mic, please. Hello, Amel. Okay, let's start. Okay, good. Let me put the chat here. So, today we have graph. Graph, I have no idea what it is, but let's learn together. Let's start from here. A graph is, I'm sure I'm recording or not. Okay, I'm recording. So a graph is a structure containing a set of objects, node, or vertices, where there can be edge between these node and vertices. Vertices. What do you say this?
Vertices.
Vertices. Edge can be directed or undirected and can optionally have values. A weighted graph. Tree are undirected graph in which any two vertices are connected by exactly one edge, and there can be no cycle in the graph. Okay, tree are undirected graph in which any of two vertices are connected by exactly one edge. Okay, so when there's one edge, it is undirected. Edge can be directed or no, that not, I guess. Okay, and can optionally have value. Okay, graph are commonly used to model relationship between unordered entities, such as friendship between people. Each node is a person, and each edge between nodes represent that these two people are friends. Distance between location. Each node is a location, and the edge between nodes represent that this location are connected. Okay, and the value of the edge represent the distance. Okay, I still don't understand well, but I did.
Oh,
yes, go ahead, please. Yes.
Okay, so you can imagine maybe your own country, yeah? You have many cities, right? The cities would be the nodes. And then the distance between the cities would be the edges of the vertices, which would have values. So I don't know, maybe from Marrakesh to Ket or something would be a certain amount of kilometers. So Marrakesh would be a city, and then Ket would be another city. And then to get from Ket to Marrakesh, if it's a direct route, then they'd be connected, right? If there's a road between them. But if there isn't a road, sometimes, you have to go to one city to get to another city. That would be three different nodes represented by the cities, and then the roads, the actual tar on the road would be the edges between those cities, the connections between those cities. And then in terms of the direction, sometimes you can have graphs with one direction, or you can have them with two directions, i.e. you can go to Marquez and then you can go back to another city, so it'll be bi-directional. But sometimes you only have a single directional node, i.e. it's only a one-way road that you can go through.
Okay, that's made it more clear to me. Thank you. So I guess if I can repeat, if I understand well, so we have undirected or directed, which mean the flow of like maybe information between each node. If it is going only one direction, then it's wait, is it
directed? Yes,
directed,
you're
right? But
yes,
undirected, it mean
you can go both ways.
Both ways. Okay, I see. Friendship between people. Each node is a person. Edge between node represent that these two people are friends. Okay, so cities is the node, and the distance between, for example, you said this city and city, like the road, is the edge. Okay.
Yeah, that it would represent the distance, yeah, in that particular example. And then with the friendship, you could imagine you on Facebook as Nux, the amount of people you have connected to you, the amount of friends you have would be a graph as well. So you could represent you as the central node, and then the people who are connected to you as your friends.
Okay, this made it more clear. Let's see, graph representation. By the way, I did the. So what I do is like each section, I make it like more clearer. And the example you said about city is actually also here, so it's gonna like cool to read it. So a graph is mathematical structure. Let me zoom so it doesn't scream. A graph is mathematical structure that model relationship between objects. The objects are represented as node or vertices, and the relation between them represents as edge. Here breakdown. Node vertices, these are fundamental units of graph. They represent the object in the graph. For example, in social network, each person will be node. Edge, this represents the relation between the nodes. Edge connect two nodes. For example, in social network, edge could be representing friendship between two people. Directed or undirected graph. In a directed graph, edge have direction. For example, in Twitter network, if a person A follow person B, there will be a directed edge from A to B. In undirected graph, edge do not have direction. For example, in Facebook network, if person A is friend with person B, there is undirected edge between A and B. Weighted graph. In a weighted graph, edge have value associated with them. For example, in graph representing a road network, the node could be cities, and the edge could represent the roads between cities. The weight of an edge could represent the distance between two cities. Okay, so this is the same example. It may get more clear. A tree is a special type of graph. It is an undirected graph in which any two vertices are connected by exactly one edge. Furthermore, there are no cycles in a tree. A cycle exists in a graph if there is a path from node to itself. Okay, so a graph is just a concept. It can be a tree, it can be a matrix, it can be anything that have a node and edge. Okay. Let's see. Different way represents graph. Adjacency matrix. This is a 2D array where the cell at the let's say ETH row and GTH column represents the edge between node E and G. If there is an edge between node E and G, the cell EG will be 1. Or the weight of the edge in case of a weighted graph, otherwise it will be 0. This representation is good when the graph is dense. There are many edges. Example, there are many edges, but it's not efficient for sparse graph. Example, few edges, because it uses a lot of space to represent a few edges. Okay, so this is a matrix. We have also hash table, adjacency list. Okay, let's keep reading. I will post this link if someone wanna read it later to not bore you guys. Where is it? Make sure I share it. Okay, so after we have idea about graph, there are also here resources if you want to check them out. Okay, the graph representations can be matrix, can be like adjacency list. I want to see this how it can be graph. Okay,
Remember when we did the example yesterday?
oh, the one that was middle that I said, like that is adjacency list.
Yeah, that thing that they used to represent the tree was an adjacency list.
الملاصقة.
Okay, how do I pronounce this?
adjacency.
Adjacency. Okay. Adjacency list. There's also hash table. Using hash table would be a simplest approach during algorithm interview. In algorithm interview, graphs are commonly given in the input as 2D matrices where cells are the node and each cell can traverse to each adjacent cell, up, down, left, right. Hence it's important that you be familiar with traversing a 2D matrix. When traversing the matrix, always ensure that your current position is within the boundary of the matrix and has not been visited before. Okay, so depth first search algorithm, breadth first search algorithm, the same O, but this one is new. I never see it. I think this one what we did yesterday, DFS and the BFS, but this one I have no clue. Let's see, thing to look out for during interview. A tree like diagram could very well be a graph that allow for cycles, and a naive recursive solution would not work. In that case, you will have to handle cycles and keep a set of visited nodes when traversing. Ensure you are correctly keeping track of visited node and not visiting each node more than once. Otherwise, your code could end up in infinite loop. Corner case, empty graph with one or two nodes, disconnected graph with the cycles. Graph search algorithm. Common, breadth first search, depth first search. Uncommon, topological sort, Dijkstra algorithm.
Dijkstra, but it has so many pronunciations, but yeah.
Dijkstra algorithm. Almost never. Okay, 1, 2, 3, 4, 5. 4 algorithm. But it will be cool if we can check this later.
Yeah, they're pretty inefficient. The Bellman Ford, the Floyd Warshall, and the Prim's algorithm, the Kruskal's, they're not very, how to say, optimal. But that Dijkstra algorithm, that's like a computer science guy, one of the biggest, I think. His algorithm is one of the most efficient when it comes to traversing graphs.
Which one? Floyd?
Dijkstra, the guy with the funny name. I don't know how to actually pronounce it. I think he's Polish or Hungarian or something, but he's one of the biggest computer science. Like, he's like the Einstein of computer science.
Wow. Okay, I'm curious now. Okay. Okay, this is cool. Let me check out this guy. Your interviewer likely doesn't know them either. Okay, this one, if you don't know them, don't feel bad. Okay, this one I think we understand them very well yesterday. This one is very new. I don't know what it is about. Let's see. Okay, they are explaining here depth first search. The first search is graph traversal algorithm, which explore as far as possible along each branch before backtracking. A stack is usually used to keep track of nodes that are on the current search path. This can be done either by implicit recursion stack or actually stack that data structure. Okay, a simple template for doing depth first search on matrix go like this. Okay, we have function dfs. If there is no function, return empty. We calculate the length of row and column. We have let me zoom a bit. Visited set to keep track of each node we visit. Okay, we have direction. I assume this is R for row, this is column, so probably gonna add them together here, like here. So we're gonna keep adding this so we can move up, left, down, right. So we have def traverse, another method, and we're gonna call it here. So this is gonna be recursive. So the code starts like right here. We have two loop. We go through each element in the matrix and we call the recursive function traverse. When we go to traverse, it check if this coordination of this node is already existed and visited. If it is, we return. If it is not, then we continue and we add it as a tuple to the visited. Now after we add it, we enter a loop and we're gonna loop on each one of this direction. So this one, this one, this one, this. So we're gonna loop 4 times. And we're gonna see. We're gonna have a next I, next G. So this is the row. This is colon. E plus direction 0, which is first one is gonna be this. G is gonna be direction 1, which is this. So each time I loop, I am moving in the graph like if I have graph like this, and if I am here, I'm gonna loop on this, then if it is this, then this. I'm getting these values from here, so I keep looping, and this direction allow me to move up, down, right, left, down. Okay, looping. So I have new coordination. Then I check if it is between 0 and the row, so it like the border, so it is not outside the matrix. If it is not outside the colon and the row, what I do again is I call another traverse, so recursion. So when I am here, I'm gonna call a recursion on this and this and this, and not this, like this outside bar, so this. And if this was already visited, what's gonna happen? It's gonna return nothing. But if it wasn't visited, it's gonna add it to the tuple. So the goal of this recursion is to keep adding as much as possible, or like as much as like of this direction to the visited. So basically it's gonna, if it start here, it's gonna 1 2 3, but this outside is not gonna go. Then it's gonna jump here. Where does it jump? I guess, yeah, here. So here, so this for loop is the one that's move on H1. Okay, which kinda stupid maybe, because maybe they should check here if it's already visited. There's no need to, but yeah, but I don't. No. I think if you have to go here because this is also connected to this and this and this. Yeah. Okay. Okay. So this is a deep first search. I hope my explanation was not confusing. If someone have question, you can ask. If I miss something, maybe someone can jump in at. Are still music on? What's music? Do you hear music, guys? What's music? I think there is music. Where? Hello? Any music?
No, Shaza?
Are you sure you're with us, Saja? Oh, okay. Oh, maybe I'm not sure. Okay, forgive the other arguments are for finding shortest part in graph. Not efficient for giving me so long since I done this. Forgive the other. Okay, so this one is.
Well, that's just the link. Sorry about that. I was just gonna say that those other algorithms, they do have a purpose. It's just that I've forgotten what the purpose is. It's been so long since I've done this. but they do all have a purpose.
Mm, okay, so like there's some special case that you like this algorithm, for example, gonna be the most efficient way to do it.
Yeah. Yeah, so you could imagine if you had like a map and you're representing with nodes and edges, right? You might want to try and figure out what's the shortest path to get from the node that you're at currently to your destination. Some of these algorithms will help with that, especially when you have weights on the edges, i.e., distances. It also used in networking. If anybody's familiar here with computer networking, if you're also trying to find the shortest path to send a packet, the weight would be the bandwidth on the particular connection between the networks, right? So let's say you had routers as the nodes, and the edges would be whatever medium they're on. Let's just say fiber networks, and you were trying to calculate what's the shortest path from the router that I'm trying to send this message to the destination. Then that would be calculated with something in the route table. It would be calculated with one of these algorithms based on the weight, i.e., the bandwidth of the line, to give you the shortest path to your destination. That's how your packets essentially travel over networks on the internet as well. So these algorithms are extremely useful for not only like map finding on GPS, as well as just like how your packets get through, and other applications, of course.
Okay, good to know all this, because I'm not gonna lie, I wasn't gonna check them, but now that I know they are like useful like this, I probably should have at least idea what they are useful for.
Yeah, very useful,
like-
very useful.
Yeah, you might get like a question in an interview like about some problem, and I think if you mention at least that there's algorithm that do that, even if you didn't do it correctly or solve it, I think that will be good point than saying I don't know how to do it.
Absolutely.
Yeah. Okay. So DFS is kind of clear. I am really happy that I understand this, because it was struggling to me to understand how DFS work. BFS also we saw it yesterday. Bridge first search is a graph traversal algorithm which starts at a node and explore all nodes at the present depth. Before moving on to the nodes at the next depth level, a queue is usually used to keep track of nodes that were encountered but not yet explored. A similar template for doing breadth first search on the matrix go like this. It is important to use double-ended queue. Okay, we did learn about this. And not arrays. Python list. Okay, not arrays. Python list as dequeuing for double-ended queue is O1, but it is ON for array. Okay, to use double-ended queue and not arrays. Okay, for Python list as dequeuing for double-ended queue is O1. Okay, so this is the advantage. When you use dequeue, you have this advantage of O1, not. I think dequeue use linked list. Let me see, I think I have a video about dequeue. You can check it out. Where are you? Okay, never mind, I lost the video. Okay, we can check it later. So let's see how this BFS work. So, okay, wait a second. It is kind of the same. Okay, so it is the same thing. What is changing is this part here. It's also called traverse, but here there's a while queue, and here there's this. Okay, so I noticed something is BFS always have this while queue, so we always loop through all the elemented queue until everything out, and sometimes there is a for loop inside the while queue, like we used yesterday. Sometimes there is not. So I think we know what is this. So in this part, we created a queue. This queue have tuple. Tuple have coordination the colon and the row and colon. Then we use the pop left to pop. Okay, let me maybe do. So we have queue. Now the queue is empty. Here we create the queue and we add to it E and G. Let's say 0 0. Then we pop this queue. Okay, we pop it. Now there's nothing queue, and if this coordination not in visited, we enter this F. We add it to visited. Okay, let's say it is in visited, and then we enter another for loop, and this for loop is actually the same the one that we saw above. So what it's gonna do, if we have a matrix like this, so it's gonna go loop on each direction this ones, so it's gonna loop on this one, and each time it loop using these values we move through. So if I am here, if I am in this one, when I'm gonna reach this for loop, I'm gonna get to this cell, this one. Okay, and then when I'm gonna get to each cell, what I'm gonna do here, like before in B and DFS, we add them to the visited. This time we're gonna add them to the queue. So all this cell gonna be here. Cell 1, the up and right and left. Okay, and because the while queue still have something in the queue, I'm gonna keep going to this, pop it. When I'm gonna reach it, for example, again I'm gonna add this and this and this and this. Wait, I'm gonna add this, but this one. Okay, so this condition right here, let's say if the current's not okay, so even if I'm gonna add this to this code, they're gonna add the cell that already added before, but because we have this F here, it's just gonna return empty because it's already in visited. Okay, I think anyone have question? Is it confusing? We can like explain it again. Okay, don't be shy, please. If you have question, feel free. If you wanna add something, maybe I didn't explain well, someone can jump and explain well, or try to explain better than me. Okay, totally silence. That is a good sign, I guess. Okay, so while DFS is implemented using recursion in this sample, it could also be implemented iteratively similar to BFS. Okay, we saw something like this yesterday. The key difference between the algorithm line and the underlying data structure, BFS use a queue while DFS use stack. The DQ class in Python can function as both a stack and a queue. Okay, let's watch a quick video about the queue in Python, because we see it a lot and it's better to have.
Also, could we kindly, if I may request, if you have a video for the graph traversals with breadth first and depth first, that would be also nice, just so we can visualize.
Yeah, that will be nice. Let's do it. If someone found some video, you can post it in chat, because I actually looked for them, like, but I didn't find other than 3. I didn't find the matrix. I found only tree.
Okay, I'll find one.
Okay.
We haven't yet dealt with graphs in ALX, I don't think. I mean, we've dealt with trees, but not graphs. But again, this is a very important concept. It has widespread connotations. It helps with, I think Google Maps also use something similar in that in the back end, the you know what I mean, the towns and cities and the roads are represented as a graph. And then obviously you do your things, and then obviously the relationship with friends as well, and the networking example I also gave you. There are many things in which you can basically, how to say, take a problem and then transfer it into graph form, and then after that figure out solutions based on these graphing algorithms. So it's a very important concept. We just need to see the visual representation of it to just get it home. But let me just find a video.
Okay.
So I want to
Yes,
make
go
a
ahead,
comment.
please.
Yeah, can we say graph similar to I think what was it called? It's called binary tree, like a tree that has n number of children.
Can you repeat, please?
Like, can you say a graph is similar to a tree that has n number of children? You know, there is binary tree, there is ternary tree, that's 3 children, and then there's n-nary, that's n. I don't know how to pronounce it, but it's like the number of children for the root n. Like, it can be any number.
I think
Yes.
anything that have node. Yeah, go ahead, Daniel.
So it depends on it depends on the thing that you're trying to, how to say, abstract, or the thing that you're trying to model. So let me take a simple example like the mapping, right? I keep on going back to mapping. Let's just take mapping for example, right? So a city may be connected to many other towns or no towns, you know what I mean? Which would make it a useless city. But a city can have any amount of connections or roads leading to other towns. So yes, basically you can have as many nodes, I mean edges as you want, coming out of a node to another node. There's no real limitation. It just depends on the problem you're trying to, how to say, visualize. So take networking as well, right? You're familiar with switches, right? A switch can be connected to up to, you know what I mean, 48 other devices. So that as well can be represented as the switch being the node, and then the end devices being also nodes, and the cables being the edges that connect those nodes to the switch. So yes, basically you can have as many connecting edges as you want, depending on the problem you're trying to visualize or solve using graphs.
Okay,
If
so
that helps you.
there's no particular root.
It depends again. So let's just take a city example back to the one that we're visualizing here, right? So in your particular country, you may have many cities, right? And then imagine each city being an edge, the circular things, and then the things that connect the cities are roads, right? So
Yes.
there may not be a direct route to a particular city from one city to another. There may be that you have to go through another city to get to another city, you know what I mean? So there'll be no direct route, but there'll be a route to get there in some cases, but in some cases there may not be a route to get to a city. For instance, if you're trying to go overseas, there'll be no road that can get you off the continent, you know what I mean? So problems like this are what graphs will help you solve, to see if you can actually get to that destination city from the city you start off with, and then also which is the shortest path to get to the destination as well. That's another problem that you'd want to solve using graphs.
So, I get the why you're explaining, but I'm trying to compare it to a tree, like the binary tree we did yesterday. So a tree will have a root node that we start from.
Oh yes, the root node. Oh, sorry, forgive me. I thought root is an ROUTE.
No, like a root node.
So a root is a graph, right? But it has certain constraints on it. the constraint is that the root is the beginning of everything, right? It stands at the top of the tree for a binary tree, and then it's connected in an undirected manner to other things, but a maximum of 2 children. So it has certain constraints on it, but essentially it is a graph, but with many constraints. Constraints being that each node can only have 2 children, and they should be a root node.
Okay, but that's different for a graph because it is as many children as possible, and not nodes can connect to nodes regardless of position.
Absolutely. A graph is a different, it's basic. There are many kinds of graphs, right? There are graphs where the edges, the connections can go one direction only, or they can go in 2 directions. So there are many kinds of graphs that you can represent, essentially, with those kind of constraints in mind.
Okay. I think that has given me a picture of what the graph is. Thank you.
Thank you.
Yeah. I want to say
Yes, go
something.
ahead.
I think generally a binary tree itself will also be classified as a graph. So just that most of the times when we're talking about the idea of a graph, we are looking at like kind of multifaceted connections. But normally, all we need to have a graph, the basic concept is simply a node connected to another node. But the general graph kind of have a node connected to several other more than 2. Those constraints are not there, as Nyangasi was saying. So those constraints are not there. But binary tree itself, so you don't have to limit your mind that no, a graph is just more than 2 connections. No, the concept of a graph is barely nodes connected to others. But most of the time when we're talking of graphs, the scenario is more of those small connections. So just wanted to make that clear.
Okay, I did find the video of DQ. I'm gonna play it just so you can have idea how DQ work. Ningas, if you find the video about traversal or what you said, you can play it after. Okay, this one. Okay, we can watch it after this video. Okay, let's start.
The difference between a stack and a queue is the way you retrieve elements from each. Let's use collections.deck to implement both data structures. The queue works by appending elements to one side and removing them from the other. Let's create a queue of people that simulates 3 people waiting in line. Now that we have an empty queue, I'll enqueue a woman named Mary. And I'll add 2 more people, John and Susan. As you can see, the leftmost person was the first to enter the queue, and the rightmost was the last. Since this is a queue, the person who was enqueued first should be the first to dequeue. That can be accomplished with the pop left method, just like this.
Okay, and here it was confusing before to understand, like why pop left not pop, because if we did pop, it's gonna give us Susan, but Susan entered the queue the last person, so we need to serve the first person, which is Mary. And because we are using append add to the left of the, let's say this is a queue, left of the queue, or like if it is array, left of the array. So pop left's gonna pop Mary.
So we can say pop left is for queues and pop is for stack, right?
Yeah,
All
but
right.
but it also depend which append. It depend on which append you did use, because if you did use append left, you're gonna have Mary here, and then when you're gonna add something, it's gonna add it to before. I think I'm not sure.
Yeah.
Then
I think you're right.
Then you have to use pop in that case.
But Muntaf, I
Yes,
have a
ma'am.
question.
Yes, ma'am.
Why we use the queue when we can use just list, and if you want to use it stack, pop stack, You can pop without any argument. If you want to pop as a queue in first node, you can use pop and pass argument 0. I see that in ChatGPT.
Yeah. So I think we read this one before because Q give you O1, not ON. So in the list you are using, it's gonna give you ON. You're gonna have time complexity ON, but when you use the Q, when you use the Q, it's gonna give you O1. I'm not sure where
in this case, queue in background using
linked list. It's using linked list, I believe.
Or dictionary.
But we're okay. We read it here. Okay, so a similar template for the one bread first search on the matrix go like this. It is important to use double-ended queue, which is this function right here, dq, and not array. Okay, don't use array by or list. Array is list in Python. As dqing for double-ended queue is O1, but it is ON for array. So dqing is when you wanna pop elements or delete elements from this queue. Yeah. So in array it's ON because you will have to shift all the elements. But in dq it's it like using linked list in the background. So it doesn't. Okay, let's see. I'm not sure about what I said append left to pop left, but I did watch this video before, so I think that's what I understand. Let's keep watching. So here we add Mary, John, Susan. When we wanna pop left, because it is Q, we should get Mary. So it got us Mary. Let's see this one.
Now, who is enqueued first should be the first to dequeue. That can be accomplished with the pop left method, just like this. Now Mary has been removed. Every time we call pop left, we remove the head element from the linked list.
Okay, John. Yeah, okay.
Stacks follow.
Wait, let's go back. Let's give us John. Okay, because, yeah. Let's keep going.
Stacks follow a similar idea, except we only use the head, or left side, of the linked list.
We are switching to stack now. The one before was a queue, now it is stack. And this dq function allow you to use it for stack, and you can use it for queue.
You might use a stack is when implementing a short-term collection of web pages. This linked list could store a collection of pages the user has recently visited, starting with the most recent and ending with the oldest. This is the equivalent of adding new items to the top of the stack. Let's inspect our stack.
Okay. Now, notice here I did append left. I don't know why I did append left, but I think it will be easy if you can just do append and then do pop. So I guess now you did append left, you will have to do pop left. So you add this one first. We're in stack now. So when we added append left, look, it's become in the far right of the array. Then he add the second one, it's in the middle. Then he add the last one, and the last one now is the index 0. Let's say index 0. Now when we did pop left, it removed the one on the in index 0. And because this is stack, when we gonna pop, it should get us this, the last one that's enter.
Everything looks good so far. Now, what happens when the user wants to go back to the first web page they visited? In a normal web browser, that would look like the user pressing the back button a few times. If you think about it, going back is the equivalent of removing items from the top of the stack. We can do that with the pop left method. If I call that enough times, then the only thing in our history will be the first web page. You just learned how you can use append left, and pop left methods of the deck object to simulate stack and queue behavior, implemented using a linked list. As you can see, linked lists are a great choice when you need to frequently work with either end of the list. Next, let's implement a linked list from scratch with.
Okay, not today, sir. We're gonna stop here.
As you
So, any question about the DQ? Okay, I believe it's all
I
clear.
think this function used in background doubly circle.
Yeah, I think it's choose double link. He did said it is a linked list.
Doubly circle, because if you want to in first element, you can the last element next. If you want to last element, the first element previous.
Yeah, double link list right there.
Doubly circle. What? Yeah.
Yeah, double link list using double link list.
Circle or no? Circle or no?
Circle? I'm not sure. Circle. Okay, there is no circle in this post, so I don't think so. Okay, let's.
In this use two variable in tail and in first. Two variable.
Okay,
Yeah.
I already forget if we did explain this. I think we did, right? Yeah, we did. Okay, so for additional tip on BFs and diffs, you can refer to this Let's Code post. I will post it here, and let's see what it is. Okay, so it's a post in Let's Code, brute force solution, Python solution with data explanation. Okay, for addition tips. Okay, so if we wanna get more tips, we can read this post. Okay, I will share the link in the chat. You can guys check it later, or maybe we can read this quickly. On the other hand, so brute force solution, for every point is the grid in the grid, and whether it can reach both Pacific and Atlantic, you can use standard DFS and BFS for. So I believe this are explaining this problem, but let's just see if we can learn some trick. On the other hand, we can consider the flip side. We can let the Pacific and the Atlantic Ocean flow into the matrix as much as possible using two Boolean array, one for each ocean. The results are the points that are true in both Boolean. 2q, add all the Pacific border to 1q, Atlantic border to other q. Okay, I think if we didn't read the problem, we're not gonna understand. We can go back to it later.
The short and sweet of it is the breadth first search and the DFS, they're probably not the ones you're going to want to use all the time. Reason being is because they're quite inefficient in some regards, that you have to visit like a whole lot of other things. The way that they move is not the most efficient. So that's why they refer to as a brute force. If you're trying to figure out if you can get from the Atlantic to the Pacific and you have a set of nodes representing the ways that you can move, you're going to have to visit the nodes in a very inefficient way. That's why they're referring to it as the brute force method. And it's how to say, its time complexity is not the greatest. It's that 2mn. The other algorithms that we may see, maybe we might see the Dijkstra and the topological one as well. They're a little bit more efficient, I think. But I might be wrong.
Okay, I see. Okay, let's okay, we can read it later. Like let's see the next so we saw two algorithms. There's this one right here, new topological sorting. A topological sort or topological ordering of a directed graph is a linear ordering of its vertices, such as that for every directed edge UV from vertex U, vertex U to vertex V, U come before V in the ordering. Precisely, a topological sort is a graph traversal in which each node V is visited only after all its dependencies are visited. Topological sorting is most commonly used for scheduling a sequence of job or tasks which has dependencies on other jobs' tasks. The jobs are represented by vertices and there is an edge from X to Y if job X must be completed before job Y can be started. Another example is taking courses in university where courses have prerequisites. How do you say this?
You said it correctly.
Requisites.
Requisite. Here an example where the edge is an array of two value tuples and the first value depends on the second one or second
So
value.
that's, if I might just say this quickly, that's
Yeah.
another thing you can represent using a graph. Dependencies. I just wanted to mention that.
Okay, so like maybe you can find a quick graph about that.
But yeah, if you can just remember college or university or whatever, man. If you need to do a course, but it has prerequisites, i.e., other courses that you have to complete before you can do that. For instance, with us, if you need to do specialization, then you need to have completed. You need to have completed foundation, right, as a prerequisite. So in that case, for you to do it, you have to have completed the other little projects before it. So you can represent that in a graph, and then this can also be calculated using the topological whatever, I guess.
Okay, so to do this model, you will have to do zero first.
Yeah, so you have to do
Zero.
sprint 1, and then you have to do sprint 2, and then you have to do sprint 3, and then
0,
after that
6, 1. Okay, I see. We can explain the code. So we start definition graph topo sorts. We have numbers nodes. Let's see, it starts here. So we give it 4, which is the number on node, and we give it edges, which is a matrix, and we have 2 column and 4 rows, and each, the first 0 1 0 2 2 1 3 0. So it gives us this output, which means I need to finish 1, then I can go finish 2, then I go to 0 to, if I didn't do 1 I can do 2, if I didn't do 2 I can do 0. And I believe 0, to do 0 you have to do 1, and to do 0 here, no, maybe I'm understanding wrong.
for this one you'd have to draw it. It would be easy if you draw these 4 nodes.
Okay, let's do it in Excel.
If I can. Yeah, Shaz has been begging you to do Escalidro.
Okay, let's miss. Okay, hope it's clear. So we have 0 model, and we have 1, 2, and 3, and this one depend on 1, and 0 is depend on 2.
Maybe you should draw them. Draw them as circles, perhaps.
Yes, vertices and edges.
Like a tree.
Yeah, so you've got 4 nodes, right? And
Okay.
then one of those nodes is 0, and then you have another node which is 1.
1.
Then you have another node which is 2. And then you have another node which is 3. This is the total of the 4
Okay.
nodes that they have. And then you have the 0, 1. So yeah, 0 is connected to 1, and then 0 is also connected to 2.
To 2.
And then 2 is connected to 1.
2 connected to 1.
And then 3 is connected to 0.
3 connected to 0.
Yeah.
Okay, so this, okay, let's see how it's gonna work. So from collection we import DQ, we have nodes, order, and queue. Here the first one nodes is gonna be a hash table. Let me zoom.
I think you can use like hash table. 0 in front end 0, 1 and 2 in front end 1, nothing. 2 in front end 2, 1, 3 in front end 0. Are you understanding?
Okay,
Like hash
they are using all the types of possible, not just hash table, I believe. So they are using hash table, list, and queue to like solve this problem. So at the end, this should be 1, 2, 0, 3. Now let's try to understand this code, how it works. So this is what is called the topological sorting, right? Now we have the first one, nodes, which is the number of nodes we have. We have 4, and we send it the matrix that have the, what is called, we call it like node number with dependencies that it depend on. And so for 0 it depends on 2 node, so we create one array for that and second array for the other node, and 2 depend on 1, 3 depend on 0. So they create empty let's say what's it called, dictionary, empty list, empty queue. What we're gonna return the order. So order is gonna be list is the what we're gonna return. So this is the goal at the end of this code, and the nodes is just empty hash table. So they did 4 nodes ID in range num nodes. Num nodes is this one, which is number 4. So this for loop gonna loop 4 times. It's gonna loop 4 times, and the range is, if you give it 4, it's gonna start from 0 to 3. So 0, 1, 2, 3. So this node ID is gonna start from 0 to 3. And then I'm gonna go in nodes. Node is hash table. I'm gonna create new key with node ID, which is gonna be 0, 1, 2, 3. And each key I create, I give it this value. So this value is also a dictionary that have 2 elements, one in, one out. And out is set in the start is 0. Okay, after I loop 4 times and I create this hash table, I'm gonna have like each one a dictionary. Okay, doesn't make any sense now, but let's keep going. Now each one have this 0, 0, 0, 0, and set. Okay, now after we do that, we're gonna loop another time. This time we're gonna loop on edge. Edge is here, which is this matrix right here, and we're gonna unpack it to 2 variables. So I'm gonna have the ID 0, the index 0, index 1. We're gonna have it, so index dependencies is gonna be in the pre-ID and the node itself is gonna be node ID. Then I'm gonna go to nodes, which is this hash table, and then I'm gonna use the node ID. So in this case here it's gonna be 0. We already have 0, and then I'm gonna increment 1. So I'm gonna increment this one, it's gonna be +1. It was already before 0, so it's gonna become 1. Now nodes pre-ID. So for example, this one pre-ID is 1. So it's gonna go to this hash table pre-ID, which is 1 in this case, right? And it's gonna go to the out of the key out, and it's gonna add a node ID. So this set, so it's gonna 1. This is gonna be here a set. It's gonna add node ID 0 0. Okay, and it's gonna keep doing this for all of them. So if we wanna see it, we can do it like, okay, 0 1, and then 0, it's gonna increment it again, it's gonna be 2, and 2, it's gonna go to 2, and it's gonna add 0 here in the set, and it's gonna go to the key 2 here, and it's gonna increment it, it's gonna be 1, and it's gonna go to 1 in dependency, it's gonna add 2, so 0 2 0 2, and then it's gonna go to 3, and it's gonna increment, it's gonna become 1, it's gonna go to 0, and what is it gonna do? It's gonna add here 3. Okay, and this one is still 0, right? Because we didn't add it, and by default at start it is there.
Yeah.
So this part is finished. Now we jump to this one. This one it's saying not keys, so this one gonna bring all these keys right here, 0 1 2 3, and this for loop is gonna loop through them, and it's gonna go to each key in N and check if it is 0. This one not 0, this one is 0. Okay, it's gonna append it to Q. Okay, let's say this is our Q. Append node ID, which is, oh wait, Q? What is Q? Okay, Q, yeah. So Q is gonna be append node ID. So our node ID in this case is 1. It's appended. That's it. Okay, that's it. And then we're gonna enter this look like a BFS algorithm, this part right here, right? Does it look like a BFS? Like we have a queue, and we have this while, and we have this for loop. Yeah, this is I think BFS,
Something like it. Yeah,
Yeah.
something like it.
So we did go while lane queue. We're gonna keep looping until this loop is empty, then node ID gonna pop it. Okay, we pop it, and we're gonna go, what's happening here? For ongoing ID and node ID out. Okay, so it go to 1 in this, and it loop on this set. So it keep looping on this set of each one in queue, and it decrement. Oh, it go to the each value in set and decrement it. So 0 is gonna be minus, it's gonna be 1, the new value here, -1.
Yeah.
And if nodes ongoing in equals 0, it's gonna append. Okay, so it's incremented and check if it's equal 0. If it's equal 0, it's added to the queue. So okay, I see. And then it's gonna go again 2. It's gonna -1. It's gonna become 0. It's equal 0 now. then it's gonna add it to the queue. It's gonna become a 2 here. Okay, I think we understand what's happening. Then it's gonna keep appended.
Absolutely.
So at the end we're gonna have this array. So notice 1, 2, and then it's gonna become 0, 3. Okay, that's
I think what's key to remember here is that these problems have already been solved. They're what you call solved problems in computer science. Somebody has already come up with the solution and the algorithm for them, and they put their name on them. You just need to understand
how it
when
works.
to use it. No, when it applies. Yes, how it works, absolutely, and when to apply this particular algorithm. In this particular case, if you have a problem where you need to sort out the dependencies before you can do an actual task, and you want to figure out in what order you can solve those dependencies, then this is probably the algorithm that you want to use, and you'll probably want to use a graph to model that particular problem.
I see. Okay, Mahmoud Isa, you send this. So 0, 1, 2, 1 null, 2, 1 null, 3, 0, 1 null.
Yeah, he sent you an adjacency list.
Okay. Oh, this is for the same. This one?
Yeah, it's a representation of the graph in another form.
Okay,
Not really.
because the time is short, let's jump straight to the lit code. I think this is the last algorithm. This was a while, but I think understanding this is really important. So we have yes.
You forget hash table?
What?
Like hash table.
This one.
Yes.
Yeah, we saw one of this example yesterday, but this more like linked list because it have null at the end.
Yeah. You can use the left as array like linked list, and every index in the array you use the linked list, the right linked list. You understand? The left 0, 1, 2, 3. This will you can use this array, and everything in front end list you linked list. Like hash table was we 0, 1, 2, 3 the left the array. This the array and everything linked list.
Okay, are we ready? Let's see. So the first problem, and if you're Alex, you already done this. Okay, so number of island given an mx in 2D binary grid, which representing of map of 1 island and land and 0 water. Return the number of island. An island is surrounded by water, is formed by connecting adjacent land, horizontal or vertically. You may assume all 4 edges of the grid are all surrounded by water. Okay, I was really happy when I solved this in Alex, but when I learned this DFS, I come back to my solution and I felt sad. I'm joking, but this is completely brute force. There's no BFS, no DFS, nothing. So let's hope this time we solve it with this one of these algorithms. Let's start brainstorming. First, who doesn't understand the...
Yes, I don't understand the problem itself.
Okay.
Do we
Okay,
consider an island to be an island when it has one in all of the 4 directions, or what?
Okay, let's take it here and try to understand it together. So this is the first problem. So they are saying return the how many island we have, right? And let's get this one because it have 3 too. So this and this. Now they are saying 1 is land and 0 is water, and island is surrounded by water, is formed by connecting adjacent land. So in this case, we have one here. This is the land, right? This is the land. So this is land, this is land, this is land, 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 land. So this can go like this, can go like this, can go like this, can go like this, can go like this. So this is land 1, and there is water here, all this water, and 0 is water. So the second graph gonna make it more clear. Now we said this is land, okay, go again, okay, this is also land, okay. Now what do? I can't go here because this is not connected by this point. It should be connected by this edge. You see?
Okay, we don't move diagonal, you mean?
Yeah, this doesn't work. So we can move only like this, or like this, or like this, or like this. So go, okay. Now I check. So basically, when you are in a cell, you check your left, up, down, right. You don't check this. So 0, 0, 0. I go up. Okay, we have land. Then I keep going. Next cell, keep going. Each cell, until I reach 1. Okay. Now, when I am 1, I'm gonna check up, down, left, right. Okay, so this is isolated land. So this is number 2 land. Okay, I keep going. 1, 2, 3. Keep going until I reach here. When I reach here, I check again. I check left, right, down. So this is another land. Oh, sorry, what I'm doing. Okay, 1 is here. So there is 1 here. When I'm here, when I check 1, so this means these 2 together. So 1, 2, 3, and here is only 1. And if you notice, the way I was searching is exactly kind of this code right here, DFS and the BFS. If you notice this one also, for example, DFS, this one, I think both of them, when we were explaining them, we were like doing the same, right? We go here, then this recursion go check all the cell around it, then we go to the next one, then this next one check all the cell around it. So we can keep checking all the cell, and we can maybe okay, we can check all the cell and increment like a counter. But first, let's decide. What do you think, guys? Do we do it in BFS or DFS? I think maybe we start with.
Because you said that we are visiting the neighboring cells to see if it's 1 or not. So we are searching, or we need to check the neighbors, right?
Yes. Let me put new picture and move here. Okay, let's focus on this one because it have more case. Okay, now BFS, we're gonna go to this node and we need to check this and this and this, right? And then we're gonna go to this node, and then when we are this node, we're gonna check this and this and this and this, and we keep adding them in the queue.
But remember, we have to add them to the visited list so we don't visit something we've already visited.
We can do like a visited list. or we can change their value. The one that we visit, we change its value. For example, it's one, it become like 2, or like some other character.
Okay.
So let's try to think more. How we gonna start this? Do
Ask something.
I could
Can't imagine.
choose the code. Wait, Shaza, your voice is low a bit.
Okay.
Okay, talk now. Yeah, we can hear you now.
Okay. I say, before we are going to code, can we represent this ones and zeros with graph?
Okay,
Does
let's do
it
that.
help?
Yeah, that's a good idea. Okay. 1 and 0 with the graph. You mean like I color them, or you mean?
I mean vertices and edges, because I can't see them like a graph. I see them like matrix. So I can't think like this.
Oh, okay. So I think this is level 2. This is level 3, level 4, level 5, level 6. So you can say this is the root, and it have this node like this. Maybe something like this.
Yes, something like that. But remember, diagonal connections are not considered actual edges. So the only edges you can consider are the horizontal or the vertical ones. So that first node, of course, as you've just drawn, they would be connected to those two. And then the next two will be connected to the other one over there, but it won't be connected to the other one on top of it. You know what I mean? So the only other route would be that one. But yes, if we do it that way, I think we can, how to say, represent it the way you said.
I think you're right, but it's still hard a bit to imagine it. How we can like make it more simple? Let's ask first. Let's just remember how BFS move this like this graph. Okay, we are using DFS, right? We're gonna do it with DFS or BFS. I keep switching. Which one is simple?
Use the BFS, the Q.
DFS? The Q?
Yes,
The
BFS.
Q?
Yes. That's BFS.
Okay, DFS, the without Q.
No, I said BFS.
Oh,
not
okay, BFS.
DFS.
Okay, with
But
Q.
if you, with Q, yeah.
Okay. Now let's say we're gonna move to this node, right? We're gonna add it to the queue. We're gonna add it to the queue. 1. Now we're gonna pop it, and okay, my brain is lagging. Okay, we're gonna pop it and we're gonna add others. Okay, nice. We're gonna add other connected node to it.
Yes.
Now we're gonna add them to the queue. Let's say we add them. And same time we add them, we're gonna change their value just to know that they are visited, or you can think that we add them in a hash table or array that we visit them. So think of it like this. Think of it, I go to this node and I need to like spread, like I'm gonna spread to this, and I'm gonna pin them, right? Now can I spread to this? No, because the value is 0. Can I spread to this? No. This one? No. This one? No. When I can't spread anymore, which means there is no value in Q is empty, I'm gonna increment the, not the Q, but the like, yeah, the Q is it? I think the for loop. It's gonna be, I think, for loop, yeah. When like, let's say there's nothing anymore we can spread to, we're gonna increment the counter, right? Okay, we have one land. Now I'm gonna visit the second node, but I'm not gonna visit it. Why? Because when I was colorizing this one, I added to a variable visited, right? Or maybe I changed its value, it's not equal 1. So if it's not equal 1, I'm not gonna visit it. I go to this one, it's equal 0, I don't care about that. This one, until I find 1. I go again, start here. This one already visited. This one, until I reach here. Okay, here is 1. Okay, I add it to the queue. I add it to the queue, and then I go check all its node or like children, and then okay, all of them are 0, so I did add nothing more to the queue. So this is the loop gonna finish here, like it's gonna loop, there's nothing. But if, let's say if it was this one was 1, when it's gonna pop this one, it's gonna move to this one, and then this one gonna check all the child. So each loop its end, it means that we reach the limit. There's no more land. Then we're gonna increment we're gonna increment the counter. Then we're gonna move to this one, it's 0. No, 0, no, until I reach this one, 1. I add this to the queue, and when I pop it, I'm gonna add this too, until there's nothing in the queue. Then I'm gonna +1, which is 3. It's a bit confusing, but I think if we go to if we did like what's it called, pseudocode maybe, and start coding it, it's gonna become more clear. Or we can
Just a question.
Yes.
Is the thing is this is an array. The way I see this is an array, right?
Yes.
Like more like a matrix. Is there a way to represent matrix in a graph? Like, is there a special method to do it?
Maybe there is. I'm not sure. We can search.
No, it's okay. I'm just asking. I just want to know because this is actually a matrix. The way I see it, so like array.
It's a matrix.
Matrix. Yeah. I was thinking maybe there's a way they could represent a matrix in a graph. That would have really made it more, but it's fine. Your approach is no, it's okay as well. Yeah, it's okay.
Yeah.
So a graph can be represented as a matrix, right? What happens is you just take the number of nodes that already exist, right? Let's say there are 5 nodes. To represent the graph as a matrix, right? You have 5 nodes. They might be directed to anything anyway. It becomes a 5 by 5 matrix, right? You can imagine if you have the nodes on the y-axis and then the x-axis as well, right? And then each connection, i.e., if you can get from node 1 to node 5 at the point where they intersect, right? At the 1, 5 position, you put a 1 to represent an actual connection, if that makes sense. That's how you represent a graph as a matrix. But in this particular case, they've just given us a matrix that doesn't necessarily represent the connections. You have to essentially create the connections, the graph representation of it, and then be able to compute using breadth first search, if that makes sense.
Yeah, so you can go from matrix, from graph to matrix, but the other way around, you have to use the concepts to do it. Is that what you're trying to say? like you just said that you can convert from graph to matrix, right? It makes sense. So what I was asking was converting this particular matrix back to a graph, maybe like a tree, kind of.
I get you, but I don't think this is a representation of a graph, if you know what I mean.
Yeah, I get.
This is the representation of the island, but we want to take this representation and then turn it to a representation of a graph.
Okay, let's jump to solution, but let's make sure that everyone understand the problem first, then we ask if we... Okay, let's see. Who understand the problem? Who still doesn't understand the problem? Like, what we're trying to do. Okay, everyone know what we're trying to do, right? We're counting the land. Now, how to count, like, in the graph with our eyes. We know how to do it, right? So, as we say, this is a land, this is land, this is land. Now, to do it, there's two solutions. There's with BFS and DFS. Now we're gonna focus on the BFS, which means we're gonna use Q. We already, if we saw here, let's just see this, maybe this gonna give us another idea. So if you notice here, this is the main function BFS, but everything is happening in this traverse. This is like the BFS algorithm, right? So if you notice, they have two for loop, just to like keep moving between this. You know what, let's copy this here, and so so they are using this two for loop to keep moving through the array, right? Move to the end, then go down. So he's gonna move on all the elements one by one from the start to the end. Okay, now each time he's in some cell, he's calling traverse. Then when traverse finish a job, he go again to this, he call traverse on this, again traverse on this. He keep doing that, he doesn't care about anything, right? So we wanted the same concept. Now this traverse, what it's gonna do, it creates a queue. Okay, behaviors, it creates queue, and this queue it save E and G, which is coordinates of colon and row, right? So R, let's call it E and G. A while queue, by the way, this code is not solving this problem. This is just a template for BFS, and we're gonna try maybe use it to solve the problem. So while Q, because we add this to the Q, Q is have 1, right? Probably should say 0, 0. And now we add it here, and then while Q is if you have something, which is this, I'm gonna pop this. Okay, let's pop it. It's out. Now I got the value of it 0, 0, and then I check if it's visited. So here they are using a visited let's say, what is this array set, using a set, and then if it's not in the set, they add it. So 0, 0, 0 add it to the set, and then they use direction, this technique, because when we are here, we need to reach to all elements around this node, right? So this direction right here with this for loop, it's gonna go to this and this and this and this. So they have next E and next G, which gonna be the current E and plus direction 0, which is 0 here. And each time you loop, the direction 0 gonna end, right? It's gonna end from 1, -1, 0. So each time you're gonna be checking different cell around that cell, which is this is what we want, right? We wanna check this. So each time we say if it's 1, if it is 1, or not. If it is 1, we're gonna add it to visited. Then after he calculate the new cell coordinate, he check if it is inside the border of the matrix. If it is inside the border matrix, which means he's not gonna check this, not gonna check this, he's gonna check only this one and this one, he's gonna append it to the queue. So this is the key. You go to this cell and you append this after. You append it here, you append it here. You go to this cell, you append this to the queue. So every time you go to a new cell, right, you can find the connected children to it and you add them to this cell. Now, in here, this while queue is not gonna finish until it empty this cell. So, let's do this technique on this problem and see if it's gonna work. Is it clear how the BFS move through the matrix? If someone have question, please go ahead. So our code gonna be probably similar to this. So we're gonna do maybe we keep the code. So we're gonna keep probably the same thing, and we need to add a counter, right? We need a counter. So where we will need counter? Which phase? Probably here, right? Because when we launch traverse on this, automatically after this traverse can return, I have all of this in visited. It's gonna all in visited set, right? I'm gonna have this here, this here, this here, all of them. So I finish this, I'm gonna increment the counter, then I'm gonna move to this one. I can add a check here. If this one I already visited, don't move it, go to this one, go to this one, go to this one. Okay, let's do it. I'm not sure if you guys are still with me or I'm far away. Okay, so let's code it. Okay, I hate this box right here. They could add a collapse button here, which collapses. I actually sent support message to Excalibur and they say, you know what, you can use some option here that doesn't do what I want. So let's move this to this side. Okay, so let's code it the way it have. So we have def BFS matrix, right? If not matrix, return, right? So we're gonna return an empty array. Now we have rows equal len matrix. So this is just basic stuff, so we don't need to think about this stuff, right? So 0, then visited. Let's say we're gonna use visited, so to not make it complicated. Set, gonna use set, so we don't need to check if it exists. Direction equal and then 0 1 0 minus 1 1 0 minus 1 0. Right now the def traverse.
Directions represent what? And
Wait, what I'm doing? I can copy the code. Oh my god.
The directions represent the edges. We're looking for edges, right? So you can only look for edges. Remember, you can't look for them horizontally. So you can only look for them above, to your left, to your right, and below, respectively. So those coordinates or directions is relative to where you are in the matrix. So let's say you're at the 0th position. Then you will attempt to look above you, which there's nothing. You attempt to look to the left of you, which is nothing. And then you attempt to look to the right and then below you as well. So those directions are the ones that we're going to interrogate as we move through the matrix representations of the island and the water.
If I may add, like this line right here is like the one responsible for this movement. Like right here. Notice we get the current E, which is this one, and the current G, which is this one, like this, and we add direction 0 and direction 1, right? Which is this one, 0 and 1. And because we are looping on this direction, so each time loop we're gonna use this one, next loop we're gonna use this one, next loop we're gonna use this one. And what changed? If this was 0 0 and I add 1 on the colon, it's gonna be 0 1. So this one, if I did -1 in this side, 0 0 -1, it's gonna become -1 0, which is outside the boundary. But for example here, it's gonna be this one.
Yeah, but it will be easier, right? To essentially you'll just check whether or not it's within the boundaries of the length of the array, so you don't get a out of bounds index error. So we'll be checking for that as well, because they can't possibly be something of value if it's out of the bounds of the array. So that's definitely something we'll be checking as we move along.
Okay, I think I copied the wrong code. Okay, I'm writing the code and the code is here. I can just copy it. Okay, so this is the code, right? How we can adapt it to our solution? So
essentially what we're doing, right, as we traverse the matrix that represents the islands, we want to ensure that before we move on, we've added all the possible coordinates of that matrix that represents the islands to produce one continuous bit of land. And the beauty of the breadth first algorithm, if you guys remember, is it spans out in many directions that it go until it gets to a point where it can't go anymore. Remember, in the trees it'll be to the null, but in this particular representation it'll be to the 0. So in every iteration it will expand out one more in the directions that it can do, which is horizontally and vertically, looking for ones. And then when it gets into, when it goes in a particular direction where it can't add anymore, i.e. there's 0, it's going to stop going in that particular direction, and then essentially you would have found the boundaries of that particular island that you're at the moment. And then when they've all sort of kind of stopped visiting any more new nodes, then you would have spanned out in all the directions possible to find the completeness of that island. And then you'd be assured that in that particular iteration, or in that particular loop, you found all the boundaries of the island. And then you can sort of kind of conclude that you found an island at the end of that breadth first search. And then you can then move on to the next few until you find another one that's a 1. And then you check if, wait, have I visited this island before? If you haven't, then you start doing the same thing, that you span out in the directions until you find the body of that island. And then once you found the body of that island, you can rest assured that you found another different island, because you haven't visited any of those points, essentially. So then you add that as another island, and then you do that again until you found all the particular islands in that particular matrix representation.
Now the magic part. Let's transfer this code to what we want.
Can I ask a
Yes,
question?
go ahead, please, Harper. Yes.
So, I'm trying to get a visual of what's going on. So when I visit 00 of the matrix,
Yes.
I add it to my visited
Yes.
set.
You add it to visited, and it's also in queue.
Okay. So I have that location. So when I now use the direction to search the left, right, top, bottom,
Yes.
am I adding those directions to the
To the
visited
queue.
also?
To the queue and also visited, yes. Because we don't want to
Okay.
visit them again.
Okay. That's what I just wanted to.
Because they are in the queue again, we're gonna jump. When we are still in the same loop, we're gonna jump to them to see their child. I mean this child. So we add them for queue, so the main reason why we add them to queue, if I add something to queue, that means I am always gonna check their child node. What is around. So that means I've also add this one to queue because it is one. What that mean? That mean I'm gonna add to their child, right? So notice that I am expanding somehow because I add this, then I'm add a child. So it's like I'm expanding around the matrix. So I keep expanding until I don't find any more ones, which is the land.
Yeah, you're essentially searching in the dark, but you're moving in multiple directions, 4 directions at most at a go. But you're looking for ones. Ones are the only value ones.
In this case now, after visiting 00, when we go to 01, that will be 01. When we go to 01, that means we're not going to run the breadth first search on that 01. We'll go
00 would have been 00 would have been visited, right? So you won't be checking that direction anymore. You can't go up because up is out of the bounds of the matrix. So you'd be going down. I mean, you can't go. So then you can't go right as well because right is 0. 0 again is the boundary of the island. So you're not interested in the zeros. And then when you go down, right, it's going to be, what is that? That's 1, 2. No, that's 1, 1, right?
1, 0.
No, it'll be 1, 1. No, the one below the 0, 1.
Because you have already visited 1, 0, so you don't go to 1, 0 again.
Yeah, 1, 0 would have been visited, but essentially we're 0, 1, right? It's 0, 1. If 0, 1 is the first thing we visit after 0, 0, then only 1, 0 and 0, 0 and 0, 1 will be in the matrix. So you can't visit 0, 0 because 0, 0 is already visited. You can't go up, right, because that's out of the boundaries of the matrix. You can't go right to 0. What's that? 0, 1, 2, 0, 2, so because 0, 2 is you go down, right? You go down to 1, 1. Yeah, 1, 1 is not visited, so you add that to the queue. And then after that, because it's breadth first search, right? You don't essentially go to 1, 1. I know it's confusing. You don't go to 1, 1 quickly. You have to then wait for the next thing in the queue, which is going to be the 1, 0, right? The one below the 0, 0. And then you're going to check for its neighbors, right? When you look up at 0, 0, 0, 0 is already in the matrix. So you can't, it's already been visited. So you can't go there. And then you try and go to your left. Left is out of bounds of the matrix, so you can't do that. No, at 1, 0 now. And then when you go to your right, there's going to be the 1, 1. But the 1, 1 is already in the queue, so you can't add something that's already in the queue, right? But you haven't visited it. Sorry, you haven't visited, sorry. So you're going to add it to the matrix because you haven't visited it yet. It's in the queue, but it hasn't been visited because of the way breadth first search works, right? You added the 1, 0 before you added the 1, 1. So you have to visit the 1, 1's things before you do the 1, 0's things before you go for the 1, 1. But essentially you would have added 1, 1 twice to the queue, but not to the visited. But once you visited those other ones, and then now you want to go to 1-1, you'll do the 1-1 thing, and then you'll check if you visited the other ones. Of course, you visited them, so you won't add them to the queue. But you'll only do the 1-1 thing once. And then after that, when you try and do 1-1 again from the queue, it's going to tell you, no, you've already visited this one, so you can't do it again.
So, how do you now know that you have met the island?
Because at that point, there'll be nothing else in the queue that's unvisited.
Oh, yes, nothing's in the queue again. Okay, so you can now increment the counter. Okay.
Yeah.
Okay. Yes, go ahead.
It needs to be followed and traced, but that's essentially it. The visited thing, make sure that you don't do any cyclical transactions, i.e. you're not going around in circles constantly. The visited thing is going to allow you to terminate the while loop within the breadth first search to stop you from infinitely visiting things that you visited before.
Yeah.
Okay, let me disable this.
Sorry for interrupting you, Munsif.
No, it's me. Okay, so now we have idea. I think if we code it, it's gonna be more clear. Now, we said we're gonna use this code and just adjust it to our needs because it's doing the same thing. We're just gonna try to adjust something. So let's start from here. We have for loop on 4 rows and column, which is this one. That's a length. We get the length. We have visited. We need that. We have direction because we're gonna keep jumping from the main node around the child node, so we need this direction. We're gonna keep them. And we have div traverse. Let's say when we use this traverse, we use it here. So this is our bridge for what's it called, BFS algorithm is here. So each node we're gonna launch the BFS, but we can optimize it by, like, if it's already in, I mean, okay, maybe not here, maybe in here. So I was thinking, do I need to launch on all the cell? And I thought yes, because okay, let's say this is one and this is one. Now I did this and this is visited, it's visited. Now when I'm gonna jump from this to this, it is invisited, but I have to check it because I still need this one and I still need to check this and this. So in this for loop I will keep it like this. So I'm gonna keep jumping on all of them, right? But maybe I should jump only on the one that have one.
Yes, it has to be the ones that are one and the ones that are not visited.
Yeah, okay. I think we don't need to do check visited here.
What about what you said before? Like marking it with X or something, like mark whenever you are in a particular, you just mark it out so that it to be, I think that.
Yeah, but I think it will be confusing to someone's follow. Maybe we do it like this and then we optimize this by removing visited and then just mark it with some character. What do you think?
Yeah,
or we do
that's
it
what
from
I'm saying.
because visited.
Just mark it out. So.
Yeah, I think we do it visited. It's gonna be easy. Then we can see how we can convert this code to that. So now there's a point. Do I do if it is one and it is visited here, or just? So I think we should do only if it is one, because even if it was visited, I still need to check it because let's say this one right here is visited. Oh my god. Let's say this one. Let me put this.
Yeah, I think that makes sense. That makes sense. Traversing only when it's one makes sense.
Okay, so but let's say this is visited, right? This is gonna be visited, right? So if I did also not visit. That means he's not gonna go here. He's gonna go here, right? That's correct, right? But
My understanding is that the traversal is the thing that allows you to find an actual island, right? So after
Yeah.
your traversal, right,
yes,
you would have found an island. So after you find an island, there's no possible reason to, how to say, to traverse that same island again.
Oh, you're right. Yes, yes, I see it. I see it now. So, yeah, you're right. So this traverser, it's gonna mark all this one. So actually, I don't need to go again to this, right?
Absolutely.
Okay, I see it now. If someone didn't understand it, we can repeat it. Or let me repeat this because I'm sure someone didn't understand.
Breakfast search is like a virus, right? It finds one
Yeah.
position and then it'll find it'll spread out into every single
Yeah,
space of the body of that
exactly.
body. You know what I mean?
Yeah,
It's,
yeah.
I don't know how to describe it any further,
Yeah.
but like breakfast search, it lands and then it
Mm,
spreads out. It's like colonialism. It spreads out to every
Yeah.
continent,
yeah.
every
Hmm.
piece of that island, and then after that, it's found every single part of it, the body. So after that, you don't need to then do it again because it's found. It's basically, I don't know how to say it. It's mapped the entirety
Yeah.
of that island.
Yeah. So, Layla, so like we have this for no, don't think about this code up, just this for loop here. So this for loop the role of it is to keep jumping from node to node, from cell to cell, right? All the matrix. Now, our goal is each node or each cell we reach, we're gonna get this coordinate of row and column. We're gonna send it to this traverse function or the BFS. What's this function gonna do? It's gonna add all the connected value or cell to this cell if they have one. So this is one, this is one, this is one. All they're gonna be in this visited, let's say, list or set. It's gonna add them. So somehow after this function finish, we're gonna have all this land mapped to this here. So if that's the case, do I need to do if here? That's like if I didn't do if here, the loop what is gonna do? It's gonna jump from this to this. But notice we already mapped this one, so we don't need to waste time on it. We can jump to this, which is 0. So our if statement here is gonna be 2 case. It should be 1. It should not be visited, which if it was visited, it means it's already part of a previous land that we already figured out. So let's see if
That we've discovered
discover.
in quotation marks.
So if how do
So if the node, if the row, if the grid and the matrix row column, is equal to 1
E
and
G
it's not been visited.
equal that is
And then
and
yeah,
and then this
and the tuple for row column is not in the visited set.
tuple. Okay, yeah, it is set. Okay, so it's gonna be E G not in. Okay, not in
Our visited set.
visited. Then
Yeah.
traverse. Then traverse. Okay, so far this part right here is gonna jump to this.
Are you
map.
not counting again? Are you not supposed to count?
Oh yes, we need to create a variable here that's called length equals 0 because we need to increment after this. Okay, after this function return, and when it return, it's like it's gonna say, hey, I did go to the matrix, I did find this from this coordination you give me, I did find all the one, and I did map them all to visit array. Then I'm gonna say thank you, let me increment length 1 plus call 1. Now I have one length, right? Then what this again, I'm gonna go to this current second one, but it's gonna skip it because we have this if statement. This is already exists, it's gonna to this is 0, skip, this already exists, skip. Oh, new one. Okay, this is a new one, it not map, doesn't exist and visited. It's gonna send the coordination to traverse, right? Okay, that's good. It's gonna it's like a virus, as Nigga said. It's gonna go to this one, go to this one, go to this one, go to this one. It's gonna add them to I don't think is this gonna add them?
No, it's not gonna add them because they're not
zero.
ones.
Yeah,
Yeah.
because this is 0, so it's not gonna
Breakfast
add
switch will
anything.
not add them.
Yeah. So this is gonna be the only part of length. It's gonna return, and this gonna be invisited. Then we're gonna increment length. Now we have 2. It's gonna jump again to here, skip this. Okay, it's gonna find the new one. It's gonna find this. Now, because it's like a virus, when it finds something, it's spread to all left, right, up, down. So it's gonna spread to this 0, spread to this to 1. It say, okay, I'm gonna add to this to visited because it's 1, 0, this out of boundary. So now we have third length. It's gonna return. I'm gonna increment this. It's gonna become 3. And after that, I'm gonna return here the length, which is gonna be value 3. Now let's go inside traverse and see if it's working as it's supposed to be, because we didn't edit this part of code yet. We only edit the start. Now let's start. How does traverse work? Let me clear this.
But traverse works on, I believe, a representation of a graph. That matrix is a representation of a graph, if I'm not wrong. It's not a graph. So that in this example, that matrix is a representation of the graph. But in our case, the matrix that's coming in is not a graph. It's a representation of an island. So those are two different representations. But essentially, we need the same logic. We need to transform that thing into, I think, unless somebody can prove or has a different opinion.
I see. Let's do first. Let's see if we apply it to this, are we gonna move as we supposed to do. Like for example, when I'm gonna send the coordinate of this to traverse, what if I know this function is working well, or if it's wicked and to become work well, what it's supposed to do at the end is this should be invisited, this invisited, this invisited, and it's return. Yeah, that's all. So all of this invisited and return. If it does this, that's good. It's working well. Now let's see. We already have visited here. So it creates a queue. It adds to the queue AG, the one that I sent it. I send her this one, this coordination, right? It added to the queue, and then it said while queue have something, so the queue have 0. While the queue have something, I'm gonna keep looping on all this section. Okay, now it's queue pop left, which is a normal behavior for BFS algorithm. You're always gonna pop after you add something to queue. So you pop this one, okay? What you gonna do next? When you pop it, you get the value of 0, 0, which is E and G, which is coordination that I sent. And I have current E and current G, right? And then I'm gonna do if current eng not in visited, then do this part of code. If they are visited, just skip. And we notice something here. I will never call traverse on coordination that are visit, so I can remove this line. It's useless because I have check here, right? Because I only call traverse on the coordination that are not visited.
Exactly, that's
So
true.
I can remove this. We don't need this. Now let's see. When we do we pop it, we gonna do visited at directly, which mean this coordination that I sent, I gonna add it to visited set, right? Okay. What else it does? It go to for direction. Okay, now I'm gonna use this direction. As we saw before, this direction allow me to visit all the child of the node. So this node, the child of it is this one above, out of border, this one to the left out of border, inside the border right, and the bottom. Okay, so far this is what I want. It's working fine. Now for direction and direction, okay, I'm gonna loop on each tuple inside, and I'm gonna see next. I'm gonna have next G, which gonna represent every time I loop this one here. I'm gonna do this math equation, so I'm gonna increment the current E. So if I am here and I increment colon, I'm gonna end up here. If I increment row, I'm gonna end up here, right? If I did minus, I'm gonna end up here. If I minus the colon, I'm gonna end up here. So this is basically this line, what it's doing. It just incrementing and decrementing from the tuple, so every time I loop, I'm in other side. And after I did that, okay, this line I need it, I'm gonna do a check. F0. Okay, so this is run check to see if I am in the border. If next E between 0 and the rows. We can do like if next E in range of rows. I think it's more cleaner. And then this one, if next G in range of calls. So if next E, which mean this new coordination that I found out, I'm gonna go check. Let me see if it is inside the matrix. If it's not, I don't need to go there.
Yes, it'll be out of bounds. It'll give you an index error or something.
When you do in range?
Yeah, the other calculation was fine. The between 0 and the
Is this not gonna work?
Yeah, it might work. It might work.
I think it works because
yeah, the range is from 0 to the length. Yeah, you're right.
Yeah, because range is gonna be 0 to ranges always start from 0 because we have 0 here.
Absolutely.
I think so. Okay, so let me read. Okay, so far we have this line that move, and we have this direction that check for coordination. Someone may ask, wait, why we are doing this? Why we're even moving through this and this direction? Why we are checking? Okay, remember we wanna add them to a visited list, because we are now trying to find out land. Where is the land? So all we are doing here is to find if there's one here. Okay, so here's the idea. We need to see if it is one, right? Before we add it to the queue. Okay, let me see. Okay. So we saw it is in the range. We need, I think, to add here and it's equal 1. Wait, yes? Yeah, we should equal 1 because what if this here 0? Do I add it to the queue? It doesn't make sense. Because if I add it to the queue, when queue gonna loop again, it's gonna... Yeah, it's gonna visit add, which we don't want. Oh my god. Because each time the queue loop, it's gonna do this visit add, which means we visit of 0 value, which we don't want. So we don't wanna add to the queue of value 0. So here we
first you check if it's in the range.
And then
how I'm first you check if it's in the range. Absolutely. We're just
how do I check the value of it?
You have to check if the particular location is equal to 1 as well.
Okay, so
matrix row column.
Oh my god, this is next
matrix row column equals 1.
Okay, matrix row.
Can you see the current I, current J?
Yes. Is it next? I think
Hello?
Next, right?
Can you hear me?
Test. Hello?
Yeah, next I, next J. Sorry.
Yeah,
next I.
okay, so next G. Oh my god, this code equal 1. Okay, so this mean it is in the range and it is 1. Okay, added to visited. Nice, we added to visited, sorry, to the queue, because we're gonna add them to the queue. Then we're gonna finish, right? Is the while loop gonna stop? No. Why? Because there's a new item in the queue, which is gonna keep looping. This time we did pop this, so this one is out of the queue. So this element is the first one. We're gonna pop it again. We're gonna do the same as we did here, and then we're gonna, if it's gonna add more element, that means we're gonna keep looping. At some point the length gonna stop, right? Which mean there's no more 1, which mean the queue at some point is gonna end, which mean we're gonna return here, right? When we're gonna return with traverse, it's gonna be all the length become 1, and we're gonna increment. Okay, that makes sense, but of course it's gonna be some bugs.
For sure. But that's a great attempt.
Yeah, let's copy this. Oh, we still need to change matrix, I believe. But maybe I change this from a matrix.
It can be called matrix, it's no problem.
Okay, so div, this gonna be inside. Okay, it does just current E.
Just make sure the return is at the right location. Yeah, the return is just a little bit too indented.
Okay, F4. Okay, so matrix, we're gonna call it matrix. Now, if not matrix, row colon length set length 0. Wait, this one should be inside BFS? I believe so.
Yeah, but you'd have to reference.
Remove this. This is our BFS, right? Yes.
Yeah,
this is our BFS. Local self, right? So
I think you have to indent everything under the
on here. Oh yes, you're right.
Yes.
Right. So from road index all gonna be
Yeah, and then if it's not a matrix, you want to return something like 0, maybe. I don't know, a -1.
here. Let's see what the So we are returning the land. If not, maybe 0. Because we're returning int. We can try. But so far everything fine. Look. Okay. Run. Do I run? Let's see. Come on. I don't think it's gonna work from first time. Of course, as I said. Now, traverse have this expected block. Okay, so I was scared. While should be because this inside the while. Okay, 4. This gonna be inside here.
That for loop as well should probably be in the function that's called at the very top.
Where?
No, the for loop from line 23. It's in the class, remember, so you can't just have it there. It has to be maybe in the top.
Okay. So
It's in the
this one is
non-misaligned
in the
function.
yeah.
Oh, sorry, forgive me. Forgive me,
It's okay.
forgive me.
It's okay. It's confusing. Probably watching from stream is more confusing. Okay, what is this bytecode style or something? Unvalid syntax. Oh, I have F here. The hell? Run. Probably gonna say F, another one. Expected an ending block after F. This. For which line? 26? Oh, this one. Oh, okay. Okay. Return here. Okay, run. Come on, please work. What the hell? Has not a bit traverse. Wait, maybe not self?
Yeah, maybe not.
Oh, it doesn't have self. This is just a function.
No, you can't use self. It's a function, yeah.
Okay, just a function.
Start.
Okay. Whew. Let's go. Work.
Yeah, it's judging this time at least.
Oh, come on, all green.
It's gonna
Let's go.
it's gonna take a long time.
What?
Seriously.
Oh, we have a.
I believe maybe it's within that if statement, the
Yeah.
visited that we removed. If we
We
can just
removed
add
something?
the visited. Remember the visited statement that we removed?
Yeah, just add it back. That's better.
Within the
Oh.
first if statement, line 16.
Oh.
Oh, not in visited. Oh,
Yeah,
we left
yeah,
it.
yeah. But isn't that make sense? Because we're not gonna add to visit.
No, we didn't remove it. I don't know why it's actually in there.
Oh, we didn't remove it.
Yeah, we didn't remove it. It's still there.
Okay. Let's see. Let's see what we have here. So we have, if not matrix, maybe this matrix I change it. That's why it didn't work. Do I need
think
to work
that's-
with same one that they gave us? Okay, let's just send it. It was great, I think. So great.
Oh, was that? Oh,
Great.
okay. Sorry. Yeah, if
Great.
that's the case. It doesn't
Great,
really
great.
change anything, doesn't it?
Let's see. Maybe the way the check it have. Okay, no, that's not the case. Okay, so we if not grid it returns 0. We have rows, colon, all this is good. Visited, set, land, 0. Okay. Now we have this. Before we jump there, let's see if this we have problem. We have this 4. Okay, this normal. We check if the grid E and J equal 1 normal and at the same time should be the the tuple E and G not in visited because visited is set and we call traverse. But for some reason this traverse doesn't return. It keep looping here. So that mean our while queue keep adding maybe unlimited, which mean maybe the pop is not working. Let's keep
You
going.
can print print in many places.
Yeah, we can print maybe here. Just make sure. Okay, wait. Before we print, maybe we see if we may notice something. So if current eng not in visited,
Because you want
visit at current eng.
where is infinite?
Wait. I don't think this can cause any problem, but let's see. For direction and direction, which is this one. Next E, next G equal this and this. Okay, we just add it, and then if next E in range, this range probably what's causing the problem. If next in range and next G in range, and grade next in G equal 1.
You can print in this if and
Here? Print.
You
I am in. Maybe we do value next.
Could you just scroll down to the for loop as well?
Yes.
Okay, no, that's fine. Sorry.
Okay, let's show how many times it's gonna do this. Run.
move the above. So yes, it's the console to above. Yes.
Okay.
Does it actually print the output to the console?
Yeah, there is. Okay, I am in.
Infinite in this function.
Spin around. Okay, so oh my god, yeah. So it's keep looping there. Okay, so this one. So what this mean? This four right here. It's keep looping on H1. But
this loop is infinite.
It might be the range.
yeah, I think this range not working. Let's do it all the way. No, in my brain it did make sense, but maybe I'm missing something. Maybe rows -1, in range -1.
No.
In range.
You were right, it goes from 0 to... just do it the old way, let's see if that changes anything.
Okay, so this gonna be 0 next rows.
You can try range in the variable and use variable here. Variable above if condition and use variable here.
Okay, let's fix it first. Let's see if this gonna fix it. If not, we know at least it's not the range.
There is infinite.
Okay, so it's not the range. Okay. Let's keep analyzing. Okay, this is a good because
Both limit. Oh,
yeah, because there's okay, let's how we can okay, we are sure this is working. So let's not double check this, but let's double check last time. So we have 4e in range rows. Range colon, we check if the grade E and G equal 1. If it is, and yeah, we might use PyTutor after if we couldn't like solve it. Let's see. So this one equal 1, and in same time it not in visited. Then we traverse. When this return, we increment length. And then we go to the next one. If it is 1 and not in visited, we call again traverse. So the problem is here. as we see. Now let's see. If the problem is here, that means this while loop probably. That's okay. So what could be the problem? Is while loop, for example, doesn't stop. If while loop doesn't stop, that means it keep adding to the loop over and over, which mean it keep added the node that we probably already treated. So maybe we are needing visited here, it not working.
I saw for this for inside if and you make this outside. Is this mistake or no? I will identify.
This one? This one? While F for F. They're all nested inside each other.
Inside. Yes.
Oh, this is the problem. Yeah, good job. You see that? Because if not visited, we should not enter here. Oh my god. Good job.
Well played, Mahmoud.
Yeah, nice. Wow. I don't think I will find out this one until tomorrow, to be honest. Ooh, let's go, guys. Good job. Nice. Hey, that was fun. Wait,
Submit, brother, submit.
I still want to see this range if it's gonna work.
Good job, bro.
Good job, all of you. Okay, run. Oh, F here. Come on, work. Okay, let's go. Let's submit this and let's clap for ourselves. Good job. Okay. We beat 30%. Not bad. I can sleep well.
Good job, brother.
Wow.
Good job,
Okay.
good job.
Okay, that's okay. Let me send you the code. It's only take us 2 hours. It's okay.
Yeah,
problem.
man, we need to understand the concepts first.
Yeah. Like now we
That's the
understand deeply.
disadvantage of copy. Yeah, that issue that guy was Mahmoud or so spotted out was because of copy and paste. That's why it's not good to copy and paste anyways. That was why he couldn't figure out the loop.
Yeah, this
What was
one, this
beneath the loop.
indentation. Yeah.
Nice one, yes, exactly.
Okay, guys. We can end the session here, or we should end it before before it's over. Thank you guys
3
for
hours. Almost 3 hours. Thank you, boss.
yeah. Thank you guys, everyone.
Tough
for your
subject.
share.
Well played.
Nice work, guys. So happy we solved this. Oh my god. Okay, see you guys.
What was the next topic?
So the next topic gonna be so we have graph. Next topic gonna heap. Saturday, yes. And yeah, it's gonna be heap. And let's see.
Heaps are just trees, right?
I
Unless I'm
believe
mistaken.
like merge, sorted, list, point to
Yeah.
origin.
I solved this problem hard.
Okay, heap
Alright.
sorts.
Yeah.
The merge
Yeah.
Okay, it's gonna be fun.
is hard.
I will do it, man. Don't worry.
Yeah, we do
See you
it.
guys.
Yeah.
Yeah, see you. Thank you,
Thank you,
everyone.
guys. See
Much
you.
love.
Yeah.
Good
Bye.
night.